Okay, so let's get started. So 2025. All right. So I'm going to recap what we did last lecture on the one-dimensional Ising model. So the question that we are trying to understand is whether you can have long-range order in a system, and so we're looking at the Ising model. And so let me go through a little bit more carefully than I did last time how we do this calculation. So what we start off with, we're saying, well, we have a Ising model, so it's a bunch of spins on a one-dimensional lattice. So here, just to help you through the calculation, because I got some questions about this. So to help you through the calculation, so here is the Hamiltonian for the system, and we're going to be summing from I equals 1 to 2n minus 1, the SI times SI plus 1. And SI can be plus or minus 1, so that's how we compute the energy of the system. Okay, so the question we're going to be asking in this part is, after last time, we realized that if I have a thermodynamic limit and I just flip a finite number of spins, that will not destroy order. In order to destroy order, you have to flip a finite fraction of this system in order to change the order in any way. And so what we're going to do is the calculation where we imagine that we flipped half the spins. So over here, I've drawn you a picture of the Ising model in one dimension, where all the spins on the left up to site n are up. All the spins from n plus 1 up to 2n are pointing down. And so in the middle, where there's a little brown wiggly line labeled B, that is what's called a domain wall. It's a wall between two domains, a domain where all the spins are up, a domain where all the spins are pointing down. So let's, let me just turn off my phone here. Excuse me about that. All right, so so what we want to do is we want to ask the question, does the system prefer this kind of configuration, or does it prefer the configuration where all the spins are pointing up, all the spins are pointing down? In other words, an ordered configuration. So the way we do the calculation is we say, let's calculate what the energy is of this configuration, then let's compute the entropy of it, then let's compute the free energy change if we started with a configuration with all the spins pointing up, and then we compared that with the free energy where half the spins are pointing up and half are pointing down. So let's compute the energy of this configuration. So on the left-hand side in region A, I've got n minus 1 terms which have minus j, which comes from this, comes from the energy over here. Then I have the term from the domain wall and the energy there, because I've got a spin over which is up on the left-hand side and down on the right-hand side. So that gives a factor of j. And then on the right-hand side, I have spins from n plus 1 up to 2n minus 1, giving a contribution minus j. And so the total energy of that configuration is written down over here. And then on the other hand, if I have the system with the spins all pointing up or all pointing down, there's 2n minus 1 terms in this Hamiltonian from something from 1 to 2n minus 1. So the energy of the domain wall is the energy where there is a domain wall, EI, and then the energy, taking away the energy of the configuration with all the spins pointing up or all pointing down, that is just 2j. So you just simply subtract these two numbers and you get the term 2j. So that's the energy cost for creating a domain wall. It's a positive energy cost. Okay, now the free energy change, though, is the energy minus the T times the entropy. So remember, free energy is the energy, or E or U, or whatever symbol you like to use, and then minus T times the entropy. So if I want to compute the free energy change, when I go from a configuration with all the spins pointing up to a configuration where all the spins point up in the left half, all the spins point down in the right half, I have to compute the change in the free energy, which is the change in the energy minus the change in the entropy. So we now have to figure out what is the entropy of the system. And the entropy of the system with a domain wall is just simply equal to the logarithm of the number of places where you can put the domain wall in the system. And that number is 2n. They can go in any one of these sites. So we have the entropy is kb log of 2n. And so what that means is that the total free energy change for sticking a domain wall in the system and flipping half the spins is 2j minus kbt log 2n. Now, what we're interested in is what happens when the temperature is some non-zero number. So we're not at the zero temperature. So temperature is something non-zero, and we're looking in the thermodynamic limit where the system is getting large. And you can see that if I have any temperature and I let n go to infinity, this term over here is going to be the one that dominates. It's going to be more negative than 2j is. And so what that means is that as n goes to infinity, for any temperature greater than 0, the free energy change is going to be less than 0. And that means that the single phase of all spins pointing up and all spins pointing down has a higher free energy than the state with the domain wall. So that means that if the system is going to minimize its free energy, it would rather be in a state with a domain wall than a state with all the spins pointing up or all pointing down. So you can say, fine, okay, so what we just discovered is that at any finite temperature, I start up with the spins all pointing up or all pointing down. Sometime later, the system will go to equilibrium and it will be an equilibrium state with a domain wall. All spins pointing up in the left half, all the spins pointing down in the right half. But now I can say, well, this left half, well, I've got all the spins pointing up. Well, I could just take that as my system as n goes to infinity. That's also a semi-infinite system, so it's an infinite system, as it were. And I could apply the same argument to that. Why would all the spins in that all be pointing up? Half of them would be pointing up and half would be pointing down. And so if I apply this argument recursively, what's going to happen is every domain with spins macroscopically ordered is always going to be unstable towards the formation of domain walls. And so ultimately, I'm going to end up with a state where there is absolutely no long-range order at all. And so what we're going to end up with is the fact that we have no magnetization and there's no long-range order in the system. So we've come inexorably to the conclusion that there's no long-range order for the nearest neighbor Ising model in one dimension. Okay, so that's the first thing. So, and we call this what we want to know then is, okay, well, if one dimension isn't going to work, the one-dimensional Ising model doesn't have a phase transition to an ordered phase. So maybe the two-dimensional one does, maybe the three-dimensional one does. We know that real magnets do have this transition. So this one-dimensional picture is not telling us what we are seeing in real life. The dimensions matter. Now, here's a historical fact. The Ising model is named after Ising, who was a student of a chap called Lenz. So sometimes people call it the Lenz-Ising model. Lenz and Ising did this calculation, the one I just did you, well, they did a slightly different one, but never mind, they got the same result, in 1925. And they said, well, there's no long-range order in this system. This is a crappy model of a magnet, and so they never bothered about it again. Okay. Of course, it turned out that the Ising model is a fantastic model. There must be hundreds of thousands of papers written on it. And Ising actually then, became a teacher, and he actually moved to America and ended up teaching in a university in Peoria, which when I used to be at Urbana-Champaign, when I was at the University of Illinois at Urbana-Champaign, that was about an hour's drive away from that. So I realized that he was there. So then I wrote to him to say, hey, I teach statistical mechanics. I'd like to tell you about, the Ising model, as it's now called. But unfortunately, when I realized this, I wrote to him. He had just died a couple of weeks earlier. So his son replied to me. And so anyway, I never got to talk to him about the model. Okay, so what we're going to do today is we're going to look at the Ising model in two dimensions. And what I'm going to show you, this is a spoiler, but what I'm going to show you is that the two-dimensional Ising model does have a phase transition. Okay, and it's very famous, and I'll tell you why. Then we're going to talk about continuous symmetries, because I want to talk about systems with continuous symmetries, and I'll tell you what those are and why they're interesting. And then I want to try at the end today to get to talking a little bit about Landau theory. So let's move on from that. I'm going to keep these pages here for future reference. So I'm going to skip ahead. This is page 28. I'm going to call this page 29. Okay. So oh, I do want to say one other comment about this result. I mentioned, so sometimes people say, oh, well, this result proves that there's no phase transitions in one dimension. Okay, that's not true. There is a phase transition in one dimension, but I'll show you what the phase diagram looks like. So here is the phase diagram of a magnet in one dimension. So the variable that I look at is the temperature, and I can also apply an external magnetic field. So the question is, what is the phase diagram of the 1D Ising model? And we've really worked it out, but you won't really you may not really realize that we've worked it out. So what we've just worked out is this: if I'm at 0 temperature, then I can have long range order. All the spins can point up, or all the spins point down. That minimizes the energy. So I know over here at H when there's no external field, just up here I can have the spins all pointing up, or over here I can have all the spins pointing down. So at 0 temperature, there definitely is there can be a phase transition, a discontinuity in the magnetization, but then at higher temperatures there's no phase transition. So that's the phase diagram for the one-dimensional Ising model. So what it means is if I go across this line here, I'm going to draw it like that. Remember the magnetization. The magnetization is equal to plus magnetization per spin, which is what m is +1 if h is going to 0 from above, and it's -1 when h is going to 0 from below. So there's a discontinuity in the magnetization. And the magnetization, remember, we calculated that last time. That is 1/n dF by the external field. So what that means is that there is a discontinuity in the first derivative of the Helmholtz free energy. And that means, therefore, using Ehrenfest classification of phase transitions, that this is called a first order phase transition. And this is a first order phase transition at T equals temperature. And just in the nomenclature here, so what Ehrenfest in the early part of the 20th century, 1916 or something like that, said if there is a discontinuity in a nth order derivative of the free energy, then we call that an nth order phase transition. And at that time, he thought that the only thing that could happen, the only way you would get singularities was discontinuities in derivatives. So that's all that he did. This classification is completely wrong, okay? Because we know that you can have all sorts of other non-analyticities other than discontinuities. So most of the interesting phase transitions are called second order phase transitions, like ferromagnetism, like superconductivity, superfluidity, and so on. But in fact, they don't have any discontinuities. They actually have divergences. Quantities go to infinity with power law behavior and all sorts of stuff like that. And that's what we talked about in the phase transitions course last quarter. So the phase diagram of the one-dimensional Ising model is really very simple. There is just a discontinuity across this axis at 0 temperature. Now, some people say there's no phase transitions in one dimension, so there is one at 0 temperature, okay? But then they say, apart from that, there's no phase transitions. That's also not true. this, notice in my statement on the left, in the little box there, I say there's no long range order for the next nearest neighbor Ising-Model in one dimension. Nearest neighbor Ising-Model in one dimension. Nearest neighbor Ising-Model. Suppose I'd said, well, okay, maybe the spins can interact not just with their neighbors, but their neighbor and their next nearest neighbor. Like that definitely happens. Quantum mechanically, that happens. Okay, does that have a phase transition? It turns out it does. So no, it turns out it doesn't. Okay, but you could create examples where the interactions between spins are very long range, and in that case, you can have a phase transition. So really, the statement is that there can be phase transitions in one dimension, but only if they're long range interactions. Okay, so the other comment, if I take this J, S I S J, if I replace that by a more general model, which looks like this, I and J, and then there's a matrix Jij, and then Si Sj, like that. So that could be a Hamiltonian, which is a more general one than the one I wrote down. And let's suppose it were the case that Jij was actually J as a function of the position of spin I minus the position of spin J. So it depends on the distance between them. And that could be something like a J naught divided by Ri minus Rj to the power sigma. So that would be an interaction that you can imagine. And in fact, there's situations where that is appropriate. And then you can ask question, what happens in this case? And the answer is it depends on sigma. So here's, I'll tell you the result, but I'm not going to demonstrate it for you. So if 1 is less than or equal to sigma is less than 2, then that means you can have long range order, even in one dimension. So if you have a long range interaction, what happens is the energy of this domain wall is not just a multiple of J. It actually can be very long, can be large and scale with n. And because it scales with n the size of the system, it can compete with the entropy. So you can violate the fact that the entropy always wins by having a very long range interaction. So this is a long range interaction. In that case, the energy scales with n in some way. So can compete with the entropy going like log n. So if the energy is just a constant like J, it can't. But if the energy scales with n in a certain way, then it is possible to have a phase transition. So the long range nature of it is what enables that to happen. Then if sigma is greater than 2, so the higher is the value sigma, the quicker this interaction decays. So we can say the interaction decays fast. And in this case, long range order is not possible. Okay, so those are the cases. And then you might say, oh, well, there's another case that you didn't mention. What about if sigma is less than 1? Okay, I've got 1 is less than, 1 is less than sigma less than 2. I can have long range order. What about this case? What do you think happens in this case? Say it again. So if sigma is very small, you think that it could be ordered. Okay, thank you. So that's one suggestion. So for not less than sigma less than 1, it also could be ordered. Okay, that's possible. Anybody else got any other comments? Any other suggestions? What could happen?
Is the energy going to diverge?
Yes, very good. The free energy diverges. In other words, what that means is that the thermodynamic limit doesn't exist. So why do we care about that? Well, we expect that the energy is additive and the free energy is additive. So we expect that if I take the limit as n goes to infinity of the free energy of the system over n, then that should be the free energy per unit volume. And that should exist. And that's what we mean by the thermodynamic limit. But if sigma is smaller than 1, then the integrals diverge and it doesn't exist. So it's not a good model of a physical system. All right, so let's move on. So let's go on to looking at what happens in 2 dimensions. So here's a situation in 2 dimensions. So let me draw a picture. We're going to try to use the same kind of argument, but it's going to have to be slightly different. It's going to be slightly different because when we talk about domains, fixed fractions of spins, in 1 dimension, they were just all the spins over here, all the spins over here. But in 2D, they can form a kind of blob. So you could imagine that if this is my system, then what I have in here is, say, some blob like this, where all the spins here are pointing up, and then all the spins around that are pointing down. So this is a domain of plus spins, up spins in a background of minus spins, spins pointing down. And so now what we have to do is we have to do the same kind of argument, but now we don't just have one interface between the positive and negative domains, we have this whole boundary like that. So what we're going to have to do is now work out the free energy of the system, when the free energy cost to create this boundary. So the strategy that we're going to do is that we're going to examine what is the free energy change introduced by having a domain like this with a boundary. And that boundary, we will call it a domain wall. Okay, very imaginative name. Okay, so let's do step 1. So step 1, we're going to do the same kind of thing. We're going to compute the energy cost. So let's assume that the boundary length, the domain wall length, is n. Then delta E, the change in the energy, is then just 2jn. Okay, so that's the same as we had before. On either side of the boundary, you get an energy cost of 2j. There's n of these bonds, and so we're going to get 2jn. So that's the energy. Okay, step 2. Let's compute the entropy. So now we have to ask the question, well, all right, what is the total number of ways to draw the boundary? That actually doesn't turn out to be such an easy question to answer. So I'm only going to show you a kind of bound for this, an estimation of it. So what we're going to do is this, we're going to estimate this. And the estimate is going to go as follows. We're going to assume that the lattice that we're on is say a square lattice or some other lattice. So assume that the coordination number of the lattice is little z. Okay, so now I'm going to say, therefore, then the boundary has n steps, and at each step as we draw possible boundaries, we can go in z different directions. So I'm going on a lattice. Let's draw the lattice. My lattice is going to be very simple. And now I'm saying, okay, show me how many ways are there that I can draw a domain wall with n steps. So you can say, well, I start off over here, and then I go in this direction, 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 and so on and so forth. And so at each step, the lattice has got n nearest neighbors that I can go to. So you say, okay, so I've got z different, not n, z different directions. And how many steps am I taking? I'm taking z. So that would say then that in that case, the total number of configurations of this boundary, this domain wall, is coordination number raised to the power n. Now, obviously, that's wrong. Okay, so why is this wrong? Okay, what is a very simple reason why this isn't quite correct, and we can easily improve it? Yeah, you've got to make sure that the edge is closed. And if the edge is going to be closed, that means that when you go in this direction, in the next direction, you definitely do not want to go backwards. Okay, right. So step 3 is to draw this a closed domain wall. You should not retrace your step. Okay, so then you say, okay, fine, we can easily solve that. We'll just replace z by z minus 1. Okay, now that's also not quite correct. Okay, but it's definitely a lot better than before, and it's not going to make a difference to the final answer. So we're just going to go with that, and it can be improved if you really want to. But as you'll see, there's really no reason to improve it. So what we've done is so we're going to replace the entropy. Then the change in entropy is going to be KB, and then the logarithm of z minus 1 to the n, and it might be a slightly different estimate, but it's going to be something like that. And so that's going to be n times kb times the logarithm of z minus 1. So z is, say, 4, so z minus 1 is 3, so logarithm of 3, some number like that. So now let's have a look at the total free energy. So step 3, so now go to step 4. So delta F is now going to be the change in the energy, which is 2Jn, minus kBt n log of z minus 1. And now we're going to do the same thing as we did before. So step 5, what we're going to do is we're going to have T be non-zero, and we're going to take n to infinity, because we're going to make this the total thermodynamic size go to infinity. We want our domain to be a fixed fraction of the system. So n is going to infinity, and the reason it's doing that is because n should be a number, should be order n in order to scale with the system size. And so then now you can see that delta F is positive if, let's see, yeah, if t is less than 2j over kb log of z minus 1. Let me, I want to write this in a different way. I'm going to confuse you. Okay, so if t is greater than this number, 2j over kb log of z minus 1, then delta f will go to minus infinity as n goes to infinity. And that means that the ordered state is unstable towards forming domains, just like we had in one dimension. So the free energy can lower itself by taking n goes to infinity with a domain wall. And so therefore the system will just break up into, will break up into domains, and you won't have an ordered state. But that is different if t is less than this number. So if t is less than tc, then delta f is minimized, not when n is going to infinity, but minimized by n going to 0. In other words, the long-range order is stable. So in other words, if I have a domain, that costs a huge amount of energy to create in the system which is ordered. And so what that means is that the change in the free energy, if you increase it, put a domain in, that energy would be higher. So the free energy with a domain is much, much greater than the free energy of the ordered state. And so that means that you get long-range order for t less than tc. So that tells you then that our phase diagram now for the two-dimensionalizing model is very different. Here's our phase diagram for 2D. So here's temperature, here's external field, and now what I've just shown you is that there's a TC, which is this, we just estimated it, KB log Z minus 1 in this calculation. And now what we have here is that there is a phase transition along this line here. And I draw it like that because, again, using the ideas that we talked about last time, if I have an external magnetic field, that will bias the spins to more or less more point up. So they're more pointing up over here, they're more pointing down when H is negative. And so what we have then is a phase diagram that looks like this. Across here, I have a first order phase transition, just as we had before. But now when I go at 0 external field, as I go down in temperature through here, I actually have a second order phase transition. And it's not obvious from what I've shown you, but it is true nonetheless, if I draw the temperature here and I draw for you the magnetization, so here is this critical temperature Tc. So what we know is that the magnetization is 0 above here, but below here, the magnetization per spin can either be +1, like this, coming in like this, or it could come in the other direction, like this. And this is true when there's no external magnetic field. Now, how you know that it's a continuous transition rather than a discontinuous one, so this is called a continuous transition. Because M is continuous. How you know that? We're not going to talk about that. That's what we talked about last time, last quarter, and I'm not going to go into the details of that here. But nevertheless, it turns out to be like that. Okay. And if anybody wants to learn a bit more about why it's a continuous transition, and even how to make a theory of the asymptotic behavior or the magnetization as you go towards TC, I can tell you that, but we're not going to do it right now. Okay, so let's just summarize this section. So the summary is pretty interesting. Whether or not you get a phase transition, you get long range order and a phase transition, depends on a bunch of things. First of all, it depends on what? Say again?
Your dimensions.
It depends on what?
Your dimensions.
Dimensions, yes. It depends on the dimension. Yep. And then what else does it depend on? Somebody else. Say again? Yes, it does depend. It does depend on temperature. A phase transition. I mean, a phase transition at a non-zero temperature. Yeah, but whether or not you get that, what else does it depend upon?
The interaction.
The range of interactions, exactly. Yeah. That's our conclusion. I'm going to just leave that there like that. I'm going to leave a space there, and we've discovered that for d greater than or equal to 2, I didn't prove it for greater than 2, but you can do the same argument in higher dimensions. For d greater than or equal to 2, you can have long range order in the Ising model with short range interactions. And so we call d equals 2 is called the lower critical dimension. Really, really bad lecturing style here. Okay. That's just a name. Okay. Now, what I'm going to show you next, it's going to take us a while to get to this result, and you're going to prove it in one of the homeworks. But this depends not just on dimension, and it doesn't just depend on the range of interactions, it depends on something else. It depends on the symmetry of the system, the nature of the symmetry. And that's what I want to go to now. I want to get on to talking about symmetry and how symmetry enters into all of this. Okay, so let's go and start a new section. So we're going to talk about continuous symmetries. So what we're going to do now, I want to talk about the discrete versus continuous symmetry. And this is described in my renormalization group book in section 2.9.2. And then also in section 5.1, where we talk about order parameters. Okay, so I want to give you an example of what a continuous symmetry is. So the discrete symmetry as in the Ising model was basically what's known as permutation symmetry, Z2 symmetry. So a spin can either go from being up to down. And it only has those two states. I can't be halfway between up or down. Okay, I'm either up or I'm down. There's nothing, no halfway thing between them. So I can't make an infinitesimal transformation. Now, when we talk about a continuous symmetry, so what I might have is a spin that points up like this, but now this spin can actually be rotated. So it is now pointing at some angle like this. So I can basically just make the spin rotate by an arbitrary angle, and not just pi, as in the Ising model. So that would be, this is actually a perfectly good model of spin systems in real materials and other things too. For example, you could say, suppose I want to describe a model of fish swimming around in space. So the fish are swimming like this, and of course they can point in any direction like this, and so they would be also described by some kind of continuous symmetry. So I will say something about those things in a minute, but I want to start off by just talking about magnets. So let's talk about the Heisenberg magnet. So in the Heisenberg magnet, it's just like the Ising model. So I have a lattice like this, but now my spins on this, instead of just pointing up or down, can be in any angle I want. So something like that. So they can be any angle. And so what I'm going to write down as the Hamiltonian for this would be the following. I'd say that the energy of the system is just minus J, the coupling constant. Then looking over nearest neighbors, I'm going to take the spin at site I and take its dot product with the spin at site J. And that would be the interaction term. And then I can have another term where I have an external magnetic field, which also has a vector character. So that's H. And then that will will interact with the spins in this way with the dot products like so. So in this case here, SI is a unit vector that can point in any direction. So that's the setup for this kind of model. And so the spin at site I then is an object that has an X component, a Y component, and a Z component. So I'll write it like that. And then I itself is associated with each of the n lattice sites of the system. So that would be an example of the Heisenberg model. And one of the things that I want to mention well, let me mention that in a minute. Let's just leave it like that for a moment. So the the interaction energy depends on the angle between neighboring spins. It's a dot product. So here, for example, if I had spins in 2 dimensions, on the 2-dimensional lattice, I can just look at the angle between them and I can construct SI dot Sj. So now we want to ask, well, what are the symmetries of this? That's the next question. And when we wrote down the Ising model, we saw that it had the spin flip symmetry, the Z2 symmetry. But here you can see that we have a very different kind of symmetry. So suppose I took a configuration of the system defined by all the set of H's, and then I now take a rotation matrix acting on each of the spins. And I rotate all the spins by 33 and a third degree. Okay, so they all go around in this direction or in this direction or something like that. The interaction energy just depends on the angle between the spins. If I rotate all the spins by the same amount, the angle between nearest neighbor spins doesn't change. And so the energy will be unchanged. So this is a symmetry. If I make a global rotation of all the spins, doesn't change the energy. Okay, so that's the symmetry classification. So now let's ask about the ordered phases. So what do we expect? So let's suppose that we're at high temperatures. Just arguing intuitively from what we already saw with the Ising model, what we would expect is that the spins can all point in random directions. If the spins point in random directions, then what that means is when I compute the magnetization, which is 1 over n, the sum from I equals 1 to n, the expectation value of SI, now it's a vector, then that's going to equal 0. So that's what would happen at high temperatures. On the other hand, for low enough temperatures, well, the spins might line up to minimize the energy. But they're not going to point like up or down like we did in the Ising model. They can point in any random direction. So it might just be that they order all pointing in this direction, or all point in this direction, or all point in this direction. So they actually have a choice. So what we would say is that at low temperatures, if there's going to be ordering, the magnetization per spin is m times some unit vector. And what is this unit vector? This will be determined by history. Why do I say it's going to be determined by history? So if you look in some books or some lectures, they'll say, I've got a bunch of spins, they can all point in random directions, there's no external magnetic field, I lower the temperature, and then all of a sudden they will point in one direction, and it'll be any one of these directions, it will spontaneously choose some random direction. That's definitely not what happens. Okay, what happens is the same thing we talked about last lecture. You might have an external magnetic field, a small one, like the Earth's magnetic field, and that will cause the spins to all point in some direction, pointing north or something like that. Then you say, okay, fine, well, I better put some shielding on. So I put some shielding on and the system still continues to point in that direction because that's how it was set up. Okay, so that's one way it could happen. Or it could happen that the initial condition to the system had a slight imbalance of spins pointing in one direction or another. And so then the system will eventually adjust itself and will point in a direction that is determined by the initial condition after a long time when the system has gone to a thermal equilibrium. So this is determined by history, either a pre-existing external field that is then removed, or it could be an imbalance in the initial conditions. So that's how we get symmetric ordering. Now, I want to talk about a very important concept right early on here, and that is the difference between different spaces. So I'll call this section which space. So what do I mean by that? Well, I have a physical space. That's the space where the lattice lives. So that might be a lattice in d dimensions, like 2 in the previous slide, could be 3, something like that. So that's the physical space. Then there's another space that I can define, which is spin space, or if you like, order parameter space. So this is the spin vector that we define at each site. That could be that could have n components, and n does not have to necessarily equal d. So this could be SI1, SI2, SI3, all the way up to SIN. So that's the dimensionality of the spin space. So I've got an n component vector. So here I've got a lattice in d dimensions, and then over here I have an n component vector for the order parameter. And so when we talk about the invariant of the Hamiltonian, so I say the Hamiltonian with some rotation vector acting on the spins is invariant under those rotations. Which space is this R in? R is a rotation matrix in spin space. We're applying a global rotation to the interactions, to the spins, keeping the interactions the same. So it's not, I'm not taking the lattice and rotating it like that. I'm keeping the lattice the same and rotating the order parameter. Now, this matters because the interplay between physical space and spin space, or order parameter space, that's the thing that gives you the richness of physical effects. And by that, I especially mean topological effects. And the topology comes in because we're going to talk a little bit about defects in the order. And when we talk about the defects in the order, we're going to see that they have a certain topology associated with them, and that affects the configurations, it affects the equilibrium statistical mechanics, it affects the dynamics. So it's a very fundamental aspect of everything that goes on here. So let's just do a quick pop-up quiz. So here's a question. So let's suppose that we apply an external magnetic field. Then to a system with a rotation symmetry. And I'm going to say that the rotation symmetry is the rotation symmetry group ON. So ON is the group of rotations in n dimensions, but here it's spin dimensions. So let's suppose I now apply an external magnetic field. So what is going to be the symmetry group now of the Hamiltonian? So let me just phrase the question. I start off with a Hamiltonian with symmetry ON, rotations in n dimensions. Now I apply an external magnetic field in this direction like this. So now my Hamiltonian has got the H term in it. Now what is the symmetry group? Yeah, exactly. It's ON minus 1. Because I can take rotations in any direction as long as they are axial to the external magnetic field. Okay, so that's the Heisenberg model. So now let me introduce to you another model. That's called the XY model. Okay, so in this model, it's just called the XY model because the spins are just, there's just two components, S1 and S2, or if you like, Sx and Sy, so there's X and Y, and so that n equals 2. And so I can say that I've got S is a function of space, X, so X is in d dimension space. And so X is X1 up to XD, where D could be 1, 2, or 3. And the interesting question, which we're going to talk about later, is as you vary N and D, there are different possibilities for order. And I want to tell you a result that's a particularly famous result. In fact, it's so famous it got the Nobel Prize. So, a result is that in the lower critical dimension for systems with continuous symmetry is D lower critical is equal to 2 and not 1. So if you go in the Ising model, if you go above 1 dimension, you will get order. So not this as in the Ising model. In systems with a continuous symmetry, you cannot have order in 2 dimensions. If you're anything above 2 dimensions, you can have order. but in 2 dimensions, you cannot. And so you will get to prove this later. This result means that there is no continuous. But actually, let me just say it a slightly different way. There is no long-range order in continuous symmetry systems in 2D for t greater than 0, finite range, etc. And this result is known as Coleman's theorem in field theory, and in condensed matter, it's called the Merman-Wagner theorem. Okay, so so you might say, okay, well, really, who cares? This sounds a bit strange. So what could be a physical application of this? So let's try to think of systems where you have an order parameter which has 2 components. So I'll start off with the easy one. So I could have a magnet, and now the magnet, instead of just pointing up or down due to lattice anisotropy, can actually rotate in a plane. So an easy plane magnet, they're called, or Heisenberg magnet. So the answer is a magnet. So that's one answer. Anybody think of any other kind of systems? And if I wanted a XY model would be called an easy plane magnet, meaning that there is a plane where the spins preferentially rotate in 2D, but they stay in that plane. So then you've got 2 degrees of freedom. Okay. Anybody think of another system that you might know about? You may not know much about it, but you certainly know of its existence, which has say 2 degrees of freedom.
Birds on the plane.
You could have birds on a plane.
Yeah, fish.
Okay, I did mention that before. You're right. So I could have a flocking of birds, say flocking of birds or fish in a plane. So that's true. They could do that. They'd be out of equilibrium, of course, because they're always moving, and that's a whole other thing, which I'm going to mention in a minute. But so that's a good answer. Something else though. Okay, I'm a card-carrying condensed matter physicist. Okay, what would I be interested in? That could be something like this. Yeah. Srijit's a biophysicist, so I'm supposedly a biophysicist, but I snuck in by deception. Yeah. So superconductor, yes, a superconductor or superfluid. Why? Okay, so this is a super interesting question. So let's just spend a minute or two talking about it. So the answer is, so I'm going to put down here superfluid, and it could be also a superconductor. A superconductor is just a superfluid where the fluid itself is charged. Okay, to interact with an external magnetic field. But a superfluid, so what do you know about superfluids? Okay, I know you don't know much about them because you haven't been taught much about them, but what do you know about them?
Undergo a phase transition, they form a condensate where there's one aggregate wave function for many electrons.
Okay, perfect. Perfect. It's just like you could be the fall guy for every question I'm going to ask in this class. Yeah, exactly. So you said all the right things. First of all, it's a macroscopic quantum phenomenon, a superconductor or a superfluid. Okay, they've got 10 to the 23 atoms. Okay, and they're all in the same state. They all behave like one. So that's amazing. Okay, that's called a coherent state. I've got I've got a wave function for a macroscopic object. Are you described by a wave function? Do you think you are? Do you think you're quantum coherent? Do you have entanglement? Do you, when you rotate around by 360 degrees, do you come back to where you are, or do you have to rotate around 720 degrees to come back to where you are? Are you a fermion or a boson? No, you're classical, right? Okay, so you're not quantum mechanical. Macroscopic things are not quantum mechanical, but superfluids are. I can have a superfluid as a big bucket sitting here like this, and every atom in it is in the same quantum state. Okay? That's what it is. So it has a quantum state, so it's described by a wave function. A wave function is what kind of number? Not you, somebody else. How many different kinds of numbers are there? Well, let's think. There's transcendental numbers, there's surreal numbers. Yes, there really are things called surreal numbers. There's integers, there's real numbers. What other kind of numbers are there? Complex numbers. Are wave functions complex numbers? Yes or no? Yeah, like wave functions are complex numbers. That's what you're taught in quantum mechanics. So these things, the analog of the spin variable is the macroscopic wave function of the system. Okay, so the macroscopic number of particles described by a single wave function. That wave function is called psi, and it has a real part, and it has an imaginary part. So I can represent it as a two-dimensional vector. So if I wanted to have, say, a two-dimensional superfluid, like a 2D XY model, I could have a thin film of a superfluid. And then we'd have a 2D XY model. Well, I've just told you that it doesn't exist. Okay, but yet people got the Nobel Prize for showing that sort of thing can exist. So the reason why it doesn't exist, but it has a different form of order called topological order. And that was that's what Kosterlitz and Thales discovered, a topological phase transition in 2 dimensions. So so a superfluid film would be an ordered state in 2D. How come? And we will talk a little bit about that later in the class. Yeah, quick question.
So in the Wolfgang theorem, you said continuous symmetry in the spin space. But here you're like, it's not a lattice anymore, right? Like when you have a
No. But at each point, it doesn't matter whether the physical space is discrete or continuous. So I can make an XY model be on a discrete lattice, or I can make a continuous model in 2D. So I'll come to that in a little bit when we talk about Landau theory. We'll talk about an order parameter that is a continuous function of space, but it has 2 degrees of freedom. So then it can be, that's how one could do that. Okay, so you're absolutely right. So what was I going to say? You just randomized me. Not your fault. Okay, it'll come back to me. Okay, so this sounds pretty exotic. So first of all, we've talked about systems with an order parameter, which is just spin up or spin down, very easy to understand. You've all seen that before. Now I've told you can have a system with an order parameter, which is a vector. Could be a vector in a plane, it could be a vector in n-dimensional space, rooted to a physical system which is d-dimensional. So that's another thing. Let me tell you another example. The example I'm going to tell you about is helium-3. Okay, so the classic superfluid is helium-4. Okay, helium-4 becomes a superfluid around about a little bit above 2 degrees Kelvin, and the helium-4 atoms are bosons, so it is a bosonic superfluid. Okay, there's another atom called helium-3. Helium-3 atoms are not bosons; they're fermions. Okay, nevertheless, they can become a superfluid. Okay, and so what we know is that below about 1 millikelvin, depending on pressure, it becomes a superfluid. And I told you a little bit about superfluids in the first lecture of this course. Roughly speaking, that means that it flows without viscosity. Then we're going to see that that's not true. But that's why it's called a superfluid. It doesn't seem to have a viscosity. It does all sorts of other things too. So it has an order parameter which is a strange object. A strange object. In other words, the Hamiltonian is invariant under transformations in the symmetry group SO3 cross SO3 cross O2 or U1, same thing. And that means this is an object with 3 times 3 times 2 components. So an 18 component order parameter. And it's not actually just a vector. Okay, it's a more complicated. I said the word vector, and it made me write down vector. 18 component order parameter. Okay. Now, why is it like this? I want to just tell you at a very, very, very low level why this is true. So I can't answer this in great detail for this course, but let me just explain to you where it comes from. So where does the U1 come from? So U1 is the group of symmetries going around a circle. So that's actually rotations in 2 dimensions. That's what U1 is. So it means I can choose the angle of a vector. So this is this comes from the wave function, the macroscopic wave function. Macroscopic wave function is invariant phase rotations. This you learned on your mother's knee when you learned quantum mechanics. I can take a quantum mechanical system, I can put it in its ground state, I can rotate the ground state by an arbitrary phase factor, it doesn't change the energy. Okay, so that means that the Hamiltonian is invariant under the rotation of phase. A phase rotation is a rotation of the symmetry group O2, which is the same as U1, which means you're just going around a circle. So that's where the U1 comes from. Okay, now here's the thing, the cool thing about this system. So what actually is a superfluid? So the answer is, well, it is actually a macroscopic condensation of bosons. They form Bose-Einstein condensation. And that's their ground state, a macroscopically occupied ground state. Okay, so you have a bunch of bosons below a certain temperature. They can order into a Bose-Einstein condensate. That Bose-Einstein condensate has, under certain circumstances, which I'm not going to go into, the properties of a superfluid. So it used to be many years ago, maybe 20 years ago, the only examples we had were things like helium-4, helium-3. Then people learned how to make colder atomic gases, and they could get atoms to form a superfluid or a Bose-Einstein condensate a nanokelvin. And so we know how to do that. So that's what a Bose-Einstein condensate is. If you have helium-4, those are atoms of bosons, and they form a condensate. Okay, but helium-3 these are fermions. So what happens in helium-3 is very interesting. The helium-3 form Cooper pairs. So what you get is a bound state of two fermions forms a composite boson. So basically, I've got the helium-3 atom here, another one like that, and then collectively, they are some kind of big boson. And then those bosons can then Bose-Einstein condense. So that happens in a superconductor. That happens in helium-3, and the question then you want to ask yourself then is, what is the angular momentum state of the composite boson? So let's think about that. I've got bosons, they're helium-3. They repel each other. They have a hardcore repulsion. And they also can attract each other, and that's how they form the boson. They have a short range spin mediated attraction. So they like to attract each other when they get close enough. They can't get too close because they have hardcore repulsion because they're atoms. And so if I have a bunch of hardcore objects trying to form a bound state, let's think about what is the orbital angular momentum state of this bound state. So what we learned in elementary quantum mechanics is that I can form a state which has energy levels, and then it has orbital angular momentum, L equals 0, 1, 2, 3, and so on. What sort of state are they going to go into? If they go into the ground state, that would be an S-wave state. What does the S-wave wave function look like? Where does it have its maximum? Say again?
The center.
At the center. S-wave wave functions look like that. Okay, but these things have a hardcore repulsion. If they try to sit on top of each other, the energy is going to be infinity. So you would expect them to not have S equals 0. So then you would say, so S equals 0 is bad energetics. So then you would say, okay, so maybe they go into the, actually this is the orbital angular momentum, so I'll say L equals 0. So actually they go into the state with L equals 1. Because that way, the wave function for any other state always goes to 0 at the origin. So the wave function equals 0 at the origin. So that is an allowed state. The L equals 0, the L equals 1 orbital angular momentum state is a state that it would satisfy the energetic constraints for superfluid helium-3. But there's another thing, okay? I told you that they have a spin-mediated interaction. So they like to have the same spin as each other, just like an Ising model does. So the spin state, because they form like a ferromagnetic state. And why this happens, I'm not pretending to explain to you. So what that means is that when I look at the symmetry group in spin space, symmetry group in order parameter space, I have SO3 for the orbital angular momentum, and I have SO3 for the spin angular momentum, and then I have my U1 for the wave function. And so that gives me my 18 component order parameter. And the physics of this system is absolutely mind-boggling. It simulates everything you see in high energy physics and so on. It's an incredibly rich system. Okay, that's where we're going to stop for today. So I'll take questions outside because there's a class in here afterwards. So let me turn off Zoom, and that's the end of today's lecture.